In reviewing your guys' online exams, the written portions, I've noticed a lot of students having trouble with problem 6. So I wanted to give a video explanation. It's a lot easier than trying to write via the Blackboard gradebook to explain what's going wrong in that problem. So a lot of students are claiming in question 6 that the transformation that you're given is linear because the zero vector is mapped to the zero vector. And possibly it would be helpful if I jotted the transformation that I gave you here. So I said with this transformation, a three-dimensional vector x, y, z is mapped to the two-dimensional vector x squared, y squared. So it's true that if we input the zero vector in R3, 0, 0, 0, that would be mapped to the zero vector in R2. This isn't actually a linear transformation, though. The first point I wanted to make, so referencing the fact that you guys, that a lot of students reference in their response to question 6, this fact that if t is linear, then t of 0, the zero vector is equal to the zero vector. The logic does not flow both ways with that statement. If t is linear, then t of 0 equals 0. And in fact, I've used the fact that t is linear in the proof of this fact. So if t is not linear, then this proof is invalid. I mean, it relies on the fact that t is linear. So you can't use the fact that the zero vector is mapped to the zero vector to prove that t is linear. Then you're changing the if and then you're reversing those statements. And that's not equivalent to what this fact says. Instead, is that you guys would use the definition of a linear transformation, which is two requirements. That when you apply the transformation to a sum of two vectors, that's equal to the sum of the vectors transformed individually. And that when you apply the transformation to a scalar times a vector, that's equal to the scalar times the transformed vector t of u. Neither one of these requirements are satisfied with this given transformation. But I'll just go to the quicker one, which I think would be the second one there. So by the way, this is the beauty of proving, well, in this case, it's something's not a linear transformation, is all you have to do is give one example of where either of those conditions fail, and then we've proven that it's not a linear transformation. So we can pick one specific example to disprove a statement like this. You cannot use a specific example to prove a general statement like t is linear. But to disprove it, we could let's let the scalar equal 2, and let's let the vector u be the three-dimensional vector 1, 1, 1. Just to keep this fairly simple. Then t of 2 times that vector 1, 1, 1 would equal t of the vector 2, 2, 2, right? That's what it means to multiply a scalar times a vector. We just multiply each component. And now I apply the transformation. So I look back up at the rule that's given for this transformation. In this case, I want to square the first component, square the second component. And that's the two-dimensional output vector. So in this case, 2 squared, which is 4, and then y squared, which is 2 squared again, 4. And that's a 4. This looks a little there. Okay, so that's t of 2 times 1, 1, 1. Now, if I do... Whoa, I didn't mean to do that. Hang on. Okay, a giant 2 times... Sorry about that. T of 1, 1, 1. Okay, so this is 2 of So if you first apply the transformation to the vector 1, 1, 1, you'll have 1 squared for the first component, 1 squared for the second component. And so this is true too. And since these vectors do not match, these are not equal, then t of 2 times the vector 1, 1, 1 is not equal to 2 times t of 1, 1, 1. So I've given a specific case here where this condition, the second condition, fails. And that's sufficient to prove that this is not a linear transformation.